All right, great. Continue, sorry.
So I showed up wanting to work on robots, and they gave me a book, and the robots were all these robot arms. And I thought, well, that's not what I want to do. I want to do mobile robots. The reason I came to Carnegie is I was backpacking with my professors from North Park. One of them said, what do you want to do? I said, well, artificial intelligence. Oh, you ought to go to Carnegie Mellon. Herb Simon just won the Nobel Prize for inventing AI. I'll tell you the truth. I had to look up Pittsburgh on a map. I had to go to the library, find out what Carnegie Mellon was. And Carnegie Mellon in the 70s was reinventing itself. It was a very good Western Pennsylvania engineering school that looked at the demographics of Western Pennsylvania and said, we're going to be a very small, very good Western Pennsylvania engineering school, and decided that they needed to go national. Now, national meant that in 1972, once a year, they would go to Chicago to try to recruit students, and every other year they would go to DC. So Dick Cyert, the president, bet his presidency on turning Carnegie into a national brand.
Yeah.
And really expanded it and grew it. He also, Cyert was a professor of business, and his doctrine was comparative advantage. Find out where you can be one of the top 2 or 3 in the world and go for it, and don't try to compete broadly. And a mid-sized university like Carnegie, that makes a lot of sense. So Raj Reddy was talking with Cyert and convinced Cyert that it was his idea, Cyert's, not Raj's, that we could be top 2 or 3 in robotics. And Raj said, but I'm not interested in playing catch up small ball. If we're going to do it, let's go big. So Cyert asked Raj to run the institute. Got $1 million grant from the Navy and got $1 million from Westinghouse. And that was the origins of the Robotics Institute.
And how important was it for him to get a big industry contract and a big public sector contract? Was that specifically the goal, to make sure they had one from each?
That was specifically the goal, is to do both. Really crack into ONR and then into DARPA, because they had a lot of money to do very interesting things. But also Carnegie has these deep roots in Western Pennsylvania. And if we could work with Western Pennsylvania industry and really help Westinghouse succeed, that was a win all the way around. This was at a time when the steel industry was visibly dying and trying to figure out what was going to save Western Pennsylvania. They thought it was Westinghouse. It turned out that was not completely the story. Westinghouse had its own financial problems.
Yeah.
But that notion of trying to see what we could do locally, what we could do with industry, as well as tapping into the U.S. government, is a big deal.
And it's interesting to hear you talk about the comparative advantage, because even Carl Compton, who ran the Princeton physics department, was MIT president for a while. He at one point wrote a letter in Science in the 40s. Essentially, he was trying to be polite as he wrote it, but he said, we see the talent going into some of the industrial R&D labs from the physics departments. We feel like maybe to the man, we have higher average talent, but we are not really touching what they're outputting. Like he thought that the firm structure and the concept of comparative advantage, organizing teams in a way that made sense, is what departments should do. It's what made sense. The concept of 20 different budgets and 20 different fiefdoms to do small research was silly. It made no sense. It's for like pure theoretician type people. But he later became an MIT president and could not succeed at that. But it seems like Carnegie, in running a lot of this, it seems like Alan Newell was calling it project style work, like the Raj Reddy style of work. It seems like Carnegie succeeded in a lot of that ethos. Would you say that's fair?
Well, so a lot of this starts with Herb Simon saying, what can we do really well? Herb was a founder of the business school, was a founder of the computer science department, was a founder of cognitive science, the psychology department. Herb then brought in Newell, and the two of them saying, how do people think and how can we encode that in a computer? That sort of set the framework for so much of what has made Carnegie successful.
Mm-hmm.
That whole AI and cognitive psych paradigm, if you look at the growth of the computer science department and then school, there's very good theoretical computer science, but the rest of it is all AI plus.
Yeah.
AI plus linguistics, and you get machine, let's see, machine translation was called. AI plus learning, and you get computational learning. AI plus human interaction, and now you get the Center for Human Computer Interaction Center. AI plus mechanical engineering, and you get robotics. So it was the combination of leadership from people like Sayre, saying, I'm going to invest a little bit of money here, and the intellectual leadership of Simon and Newell saying, this is going to be a growth area.
Yeah.
Simon and Newell, in turn, hired Raj Reddy, poached him from Stanford. That group of them hired Kanade, poached him from Kyoto. And that sort of set us off and running.
And could I read you an excerpt from Alan Newell's oral history where he talks about Carnegie Mellon's project-oriented style and Raj Reddy? Because I'd love to, he uses some terms that I'm sure you're going to hear and you're going to know I know exactly what he means. But to me, I didn't want to, I knew what I thought it meant, or maybe it's what I wanted it to mean. So I'd love to run it by you. So I'll read you 2 remarks and then I'll lead you in with the question. All right. So the first remark is he's talking about Raj Reddy's arrival and how it changed the way things were done. The interviewer asked him, you had the money along with Green and Perlis. What did you people decide to do with it? Talking about an extra injection of DARPA funds. And Newell said, I don't know, support people, just spend it. We didn't decide to do anything with it. One of the features of this environment was that it was decidedly unentrepreneurial. That seems, in one respect, like a contradiction in terms. But we never took these funds and decided we were going to go out and do big things with these funds. That was an attitude typified by the operation around here up until Raj Reddy shows up. And then remark 2 is in the 1970s with DARPA, there was a lot of changing political tides, as you're aware, and they're talking about the changing goals of DARPA when they're kind of giving out funds. And he says, and so therefore we've been pushed towards being implied. A response I have, which is not an attempt to change that is exactly what's happened. CMU has gone along with that in spades. We started going along with that in the 1970s. I can remember having a conversation with Howard Lackler as we were sitting there under the fixed funds with inflation and still trying to get an extra PDP 10. We were allowing the environment to shape us so that we were not, in fact, anything like, and we became project-oriented all in that period. We were not project-oriented in the 1960s at all. The corresponding thing is that the cats that want to play that game, the Raj Reddys, the Kanadis, and so forth, the Coons, find the game they play is how to do that and basic science at the same time within the budget. So I guess my initial question with that is, as he's talking about project-oriented, what does it mean to be project-oriented? How does that kind of differ from business as usual AI research on a DARPA grant, the way you might see in a Marvin Minsky lab or something like that?
Oh, so Minsky is a very interesting contrast. Minsky wrote this book, The Society of Mind, where you could read, it was, I don't know, 52-page chapters, and you could read it in any order, and it made just as much sense in any order as in any other order.
Yeah.
And that's kind of the MIT notion of how mind works, and how their notion of how research works is that you get 50 independent projects, and together something may emerge from that. Carnegie shows up with people like Raj, who says, I want to conquer speech. I'm going to put together a big team, and these people are going to be working on the phoneme level, and these people are going to be working on the lexeme level, and these people are going to be working on the syllable level, and these people are going to be working on the word level, and these people are going to be working on the sentence level, and there's going to be an architecture which connects them up and down, and we're going to have specialized hardware for all of this to work on. And so Raj said, let's build this project. And it was a project that had 16 different dimensions, all of which came together. Now, the Raj was also flexible enough to say, when somebody showed up and said, I've got this idea for a completely different method. Let's not bother with all of the structure. Let's just have a little system where everything sort of learns and it figures out all of those mechanisms.
Yeah.
So that was Hearsay, and that was Harpy, and that was the two different systems. And that competition between big structured AI and machine learning data intensive AI has been going on at Carnegie for the last 50 years.
And so to get very in the weeds here, I guess I'm kind of curious about, you talk about putting together a big team, and there's a lot of grad students involved in that. And it seems like on the one hand, these project oriented, to me, in many ways, it almost sounds like more of a firm structure, like firm, like company, than an academic team. And a lot of the grad students are the employees, but there seems to be some kind of balance, or the grad students are the employees, for example, with the ALV, where you have onboard grad students, or with the NavLab, but also the grad students need a thesis. And so with somebody like your thesis, I could see how your thesis would have even folded into a big team with what the project's goals already were quite well, because you were working on a specific sensor technology, and with Blackboard, you could fold all that in. But then there's somebody like Dean Pomerleau on kind of the other end of things, who obviously came later, and it's unclear how his project can mesh in with everything. Can you talk about how those management decisions are made? Because I guess the big goal of what I'm trying to do is help people understand what the CMU approach is to a management level. So this would be great.
So let me back up and say a couple more things about the big CMU picture, and then I'll talk about Dean and how we organize the NavLab in particular.
Fantastic.
The big CMU picture was fundamentally changed when DARPA sent a telegram, this tells you how long ago it was, saying that we've got $1 million to spend if you can send us a 350 word proposal by the end of the week, we'll send you $1 million.
Mm-hmm.
And that was the grant and basic research for computer science. And that grant lasted for, I don't know, 15 years or something like that. And even after that grant disappeared, that set the ethos of the computer science department, that there is this one big chunk of money, that it supports all of the graduate students, that therefore the graduate students are jointly sponsored by the entire department. So do you know about Black Fridays?
No.
Twice a year, the entire computer science faculty sits down and talks about every graduate student. And the student has written a letter, and they read the letter, and they turn to the advisor and say, what has your student been doing? And if the advisor says, well, the student is making good progress, and they did this and this and this, and it matches what the letter has said, good. Then the student gets a letter saying satisfactory progress. If the faculty member says, you know, I've been trying to work with this guy, and he's just so stubborn, he won't do what I tell him to do, then the faculty write a letter saying, you must, by next Black Friday, do this and this and this. If the student is co-advised and the one advisor says, well, I thought that Eric was working on it, and Eric says, oh, I thought Chuck was working on it. Now the faculty turn on the advisors and say, you bozos, you have to get your act together and do a better job advising this guy. But it prevents one student from being abused by their advisor. If you're not happy with your advisor, because you're sponsored by the department, you can change your advisors. But it also prevents one soft touch advisor from saying, oh, poor student, he had a rough semester. No, the entire department gets together and writes something. And there's these very carefully crafted letters of satisfactory progress, unsatisfactory progress, the dreaded N-1 letter, and then being kicked out of the department. So the ethos is that we're all in this together, that we've got some joint resources, that the graduate students are joint resources, that we need to properly take care of these students and properly supervise them. So that gives the graduate students a large amount of flexibility, but this responsibility to not just their advisor, but to the entire department. So that's great because students can find interesting projects. There is the marriage process where you walk in day one and each advisor says, here's what I'm up to, here's how many students I'm looking for. And then the students get to pick who they would like to work for. And the marriage process matches advisors who have interesting projects with students who are interested in working on them, and comes up with the initial advising list. That's very different from almost any department that I've seen any place. Almost any place, you're an indentured servant to the faculty member who happens to have graduate support. And if you don't get along with your advisor, you have the burden of seeing if there's somebody else who has money who will support you and seeing if you can switch advisors. So that has set this attitude that we're all in this together.
Yeah.
And that we'll have individual little projects, but we'll also have some of these big projects like the speech projects that a lot of people will work on. Newell himself at his height had both his human computer interaction, user interface stuff, but also his SOAR project, which was a pretty good sized project with a number of graduate students working on it, trying to figure out how they could all fit together. Newell said that you can do science in lots of different ways. One of the ways you can do it is just by doing something that's an order of magnitude bigger or an order of magnitude faster. If you can process 10 times the number of rules, then you're in a fundamentally different space and you're doing something different and the science is different.
Yeah.
If you can run your computer 10 times as fast, then the nature of the problems that you're dealing with changes in some ways that you can't even predict. And so doing something 10 times bigger is great. So he was very supportive of that kind of an attitude. Now, how did we get going on the NavLab? So I was sponsored on the original ONR project to do cool stuff. And one of the cool things that we did was Takeo build his direct drive robot arm. Another thing we did was to build this stereo vision for navigating across a room. Side notion, we were sitting there working one day, graduate students, t-shirts, empty pizza boxes, and we heard the door open and we looked over and there was Raj and President Syed arguing over who could open the door, and in walks this Navy admiral in full dress whites with all of the bet. Nobody had told us the head of ONR was coming to visit.
And is this all in the midst of, is the ALV still in full swing too? Just
this is before that. This is when I was a graduate.
Oh, okay.
So Larry Matthews, who's now head of computer vision at JPL, Hans Moravec, myself, with robots and pieces, and in walks the head of ONR to see what he's been spending money on. Like, guys, if you had told us, we would have at least cleaned up the lab and probably had a demo ready to run.
Yeah, or put on your good t-shirt.
And put on my good t-shirt. But he was impressed, and many years later I ran into him and he remembered that visit. And so he was happy to see robots. When I was finishing my thesis, we had a meeting and Takeo asked each of us, what do you want to do next? I said, you know, we've been doing a good job indoor. I want to go outdoors and really build driving cars. And when we'd gone around and said what we wanted to do next, Takeo came back and said, good, because DARPA has this money for strategic computing. They're going to be building the world's best computers, and then they need ways of showing it off. And being DARPA, they have to have a way for the Air Force and a way for the Army and a way for the Navy.
Yeah.
And the Navy is working on task force management. And that's a big operations research planning. How do you coordinate the whole Navy task force? The Air Force is working on the pilot's associate. So this is really speech understanding so that you can have an intelligent co-pilot and the pilot can talk to his, so it's speech recognition under high stress environments. And the Army wants to build a robot scout. So Chuck, you're in luck because what you want to do next is exactly what DARPA is going to have money for. So let's write a proposal for it. We had just hired a guy named Dwayne Adams. Dwayne had been deputy director of one of the DARPA offices, IPTO, Information Processing Techniques Office, and he came to be the associate director of robotics and to help us write proposals. So Dwayne said, Chuck, start writing. And we wrote a proposal for what it would take to do road following. And that was the beginning of the NavLab project. So we submitted the proposal, one for road following and one for the architecture of what the system would have to look like. I went back, finished my thesis. defended my thesis, thought I would take a couple weeks off to figure out what I wanted to do next. Raj came up and said, congratulations, you passed your thesis. There's a meeting in my office to talk about how we start the NavLab project. And that was my gap between my thesis and the NavLab project, was walking from the defense room into Raj's office to start this meeting, to start planning what we were going to do.
And to stop you for a quick second, to add to the queue of operational questions. So I have the question of grad students, employees versus novel thesis generators. And then also on this particular point, in one of the year-end reports, I believe you were, I don't know what your staff designation was to MIT, but in one of the DARPA year-end reports for the NavLab from CMU, I saw them refer to you as a project manager, which is interesting. That's not an academic designation. That sounds very industry. So I would love for you to talk a little about that too. If I should read into that or what that means too.
You shouldn't read much into that.
Yeah.
But what you should read into is when Newell and Simon and Reddy really got computer science going, and before that, Perlis and Shaw, etc. They said, if we're going to do big projects, and we did big projects like the Andrew project that turned into the Andrew file system and things like that. They said, we need to have more faculty than we have courses to teach. We can support them on soft money. So we need to have research scientists who have full faculty privileges. So if you're at MIT and you're not tenure track, you're nobody.
Yeah.
Carnegie said, no, we want to have non-tenure track people supported on soft money, but who have advising privileges and PI privileges and all of the privileges that faculty have. They just may or may not be teaching courses at this time. So unique to computer science, there's this whole research track, which is fully equivalent to the tenure track. And that was my underlying title. When I defended my thesis in, I don't know, October, Raj said, I can't make you a faculty offer. You're going to be a postdoc until July 1, and then I'll make you a research scientist. So I came up through the research ranks after having spent that 8 months or so as a postdoc. And it's partly that business of trying to figure out what research scientists were that caused computer science to break out of the Mellon College of Science and be a free-floating department, and then form themselves into a school so they could really have this parallel track. Project manager, that was just sort of a title because that's what I was doing on the NavLab project. Raj took me aside. He said, I don't care how many papers you write. I don't care how many awards you win. That vehicle has to move down the road. If you do that, you're good. I'll defend you. I'll support you. I'll promote you. So it really, because I was a graduate student writing this proposal, I couldn't be a PI. So Takeo was a PI, and I think Hans Moravec was a PI. And then as I became faculty, I became a co-PI and then eventually the PI. But it was pretty clear that Takeo was interested in the project because it was a cool project. He was also interested if he could have a few people working on individual projects, but he didn't want to worry about scheduling stuff and who got time on the machine and writing reports. So he was very happy to turn all of that over to me and let me run it the way that I wanted to run it.
And how was that? Can you describe your approach to it? Let's say describe your approach to it to somebody who knows how an academic lab works usually, but doesn't do anything like this. They output papers, they play the H-index game a little bit.
Well, you pointed out a very key feature here, that the whole system has to work and each student has to have something that they can claim as their own and that they can write up as their own thesis topic. So we got ready to put the system together, and I said, how are we going to see the road? Jill, how do you want to do it? Oh, well, she wanted to work on electrical engineering, signal processing, color classification scheme. Great, you go do that. Here's what your interface needs to look like. You need to tell me where the road is in the image. If you tell me that, Someone will take that and will steer the vehicle. Carl, do you have any ideas? I think that we ought to be able to track edges and track color features. You ought to be able to track yellow lines and track white lines. And oh, that sounds like a good idea. So Carl went off to do that. Great. If you can tell me where the road is in the image, then I'll have someone figure out how to steer it. Tony, what do you want to do? Well, I really want to steer the vehicle. Good. You can do the path planning for that kind of thing. Marshall, he was a postdoc who came over from France. What do you want to do? Well, he was a 3D vision guy. Cool. They're sending us a laser scanner. Do you think you could use that to determine where obstacles are? Oh, great. If you can find out where obstacles are, then feed that to me. Jay, what do you want to do? I think you're a good systems guy. If someone tells us where obstacles are and someone tells us where the road is, could you figure out how to put the whole system together and give them useful user interfaces? So really trying to build the system in a modular way so that each person had something that they could do and be proud of. And if it worked, great, then we plug it into the system and it runs. And if it doesn't work, well, I've got 2 other people working on other approaches to that same thing.
And then if somebody like Dean coming in with neural net, wanting to apply kind of Geoff Hinson's somewhat theoretical methods to this, how do you fold them in? Do they sit off a little further to the side in the lab? What does that look like?
Well, first of all, we said neural nets. Oh, come on. Nobody's ever built a neural net that does anything. Haven't they proved that neural nets aren't going to work? You want to try it? Sure, try it. Let's see what happens. What would you like? You want some images? We'll collect you some images. Come on in. We'll see. And then talking to our people at DARPA, because there was a different and competing office at DARPA doing neural nets and saying, look, I know you're skeptical about neural nets. We've got this neural net guy separately funded. I want to give him a shot on this. You don't mind if he uses our robot? No, that's fine. We'll disprove neural nets once and for all. So come on in and try it out. Dean turns out to be an extraordinarily bright person. Mm-hmm. You wouldn't know it to meet him, but he's extraordinarily competitive, and he's willing to get his fingers into everything. So mostly what he wanted was this recording of images and steering wheel position. And then he went off and started work on that and built a system with 100 hidden units, and it seemed like it could work, but really slowly. And so he cut it down to 50 hidden units, and it seemed like it could work as well and a lot faster. Cut it down to 25 hidden units, and eventually got down to 4 hidden units. And now he was working in a believable amount of time and still working pretty well. Cut it down to 3 hidden units, and it didn't work anymore. So, okay, 4 hidden units. Back to this theme of strategic computing and DARPA building supercomputers. One of the supercomputers they built was at Carnegie, and it was a thing called the Warp Machine. The Warp Machine had 10 pipelined units, each of which could do 10 million adds and multiplies at once. H.T. Kung was working on systolic computing, where things just sort of chunk through the pipeline. And we said, here's this big box. Because we're sponsored by strategic computing, we'll put it on the NavLab. Can anybody figure out what to do with it? Well, it's a really complicated thing and really hard to process. Dean could figure out what to do with it. Mm-hmm. Partly because Dean is a really, really smart guy. Partly because the inner structure of a neural net is multiply, add, multiply, add. You take these inputs, you multiply them by weight, you add them together, you sum it up, run it through your sigmoid function. So Dean was, as far as I know, the only person, that's maybe a bit of an exaggeration. Some of the speech people were able to use the warp also because they were doing similar kinds of things. But Dean got the full 100 megaflops of processing out of the Warp Machine. And then put it onto the NavLab, and we got the whole thing to work. So after that, Jill got her thesis for doing her thing. Carl got his thesis for doing his thing. But Dean's neural net seemed to work in most situations better than either Jill's or Carl's one. And so that's the one that got all the attention.
And then what did you consider a bigger practical breakthrough? There's obviously the ALVINN system, which to a modern machine learning engineer's eye would give them a little tear. They're like, wow, it's so minimalistic. It can do all this. And then Ralph comes around, which is it's a little more manual and things like, did you consider Ralph a much bigger practical step? Or once ALVINN came around, did it seem somewhat clear to you that something like Ralph would be possible and potentially better?
Well, so that was part of it, but the other part of it is, how do you take something like ALVINN, which at its core is just turning steering wheels?
Yeah.
It's not doing any representation of the world.
Mm-hmm.
How do you take that and merge that with obstacle detection and avoidance? How do you take that and merge that with a map? And so layering architectures on top of this that can take something which shouldn't really have a geometric representation and extract some sort of a geometric representation so we could do other things with it. That was really the fun part of it. The
Is that when it
NavLab
became a proper all hands on deck CMU type project? Kind
Yeah.
of going from ALVINN to Ralph. It sounds like ALVINN was not a one-man job, but smaller, but then maybe Ralph became a proper CMU systems effort.
Well, so Todd came along and worked with Dean, and part of what Todd did was to say, how do you get some geometry out of this so that you can train multiple different neural nets and switch between them?
Mm-hmm.
So that's even separate from Ralph. That was still in the ALVINN stuff. How do you train this thing up and have things work together? But if you look at the NavLab 90 videotape, where we're going from my house to Keith's house, that was the obstacle detection and stopping. That was landmark recognition. That was the annotated map saying when we're supposed to do what. That was high accuracy dead reckoning when we were doing a sharp turn and ALVINN couldn't work. And getting all of those system pieces to work together was a lot of fun. And this is on top of an experimental vehicle where you never knew what things were going to break.
Yeah. And then to put something on the record, you let me know if I'm wrong. So I think if some of my readers read what you said, they would say, oh, how fortunate that CMU had the systolic array going on and that it happened to be able, obviously some structures were somewhat specialized back then. It happened to be able to work with the natural language understanding project and the vision project. So my reading of the history is, first of all, this was a period when a lot of people weren't pursuing building machines at universities anymore. Obviously, this is not long after Slotnick and U of I, and Slotnick's gone on the record even 5 years before saying the era when you could build big, good machines at a university is over. Like this is for industry now. It's not for university to do. It seems like CMU systems approach kind of helped prolong the era where you could build a good workable machine at a university. And also I read that they made sure that maybe this was them just saying something after the fact. It seems like they made sure that their machine could work with the other ongoing CMU systems efforts like vision and like natural language. Is that fair, or is that me giving too much credit to the CMU structure?
Well, so the CMU structure, when I got there, they had just finished building CM Star, and before that, C.MMP. The CM Star was a powerful array of 50 PDP-11s. But the difference between C.MMP and CM Star was they were playing with, if you have multiprocessor systems, do you connect a big crossbar switch with every memory connected to every CPU, or do you connect them in some sort of a hierarchy? And so this notion of building big systems, big hardware systems, was there. And of course, computer vision has always been a hog for CPU cycles. So in the early days, they built these systems, and then they said, computer vision people and speech people have at it. Because the computer vision people and the speech people knew that we needed the cycles, and we were willing to put up with a fairly klutzy interface. in order to see if we could take advantage of these sorts of things.
Yeah.
So that ethos was there. The names C.MMP and CM star come out of the Newell and Sawarek book. So here's Al Newell, a pioneer of AI, writing a textbook on computer architecture because he understood that AI needed multiprocessors in order to work. So that ethos was there. We had a guy in the computer vision group named Rick Rashid, who was working on how you make the hardware more efficient and how you make the software more efficient and how you build microkernels. And he's the guy who went out and started Microsoft Research. So there's this long history of computer vision people having to have the highest possible processing power and being willing to put up with a fair amount of klutziness in order to take what a wire wrapped prototype and really use it for high performance.
Yeah, even to this day.
Yeah.
And okay, so this has all been fantastic. All right, so I guess one more higher question, because I'm sure I'm imperfect. I didn't ask all the right questions. Is there anything else you think people should understand about how CMU managed its projects? It was a quite exceptional contractor there for a while. To give you kind of the context for my pieces. So I've made my name writing a lot about the industrial R&D labs. And the reason I've done that is because you have a lot of these Silicon Valley folks who, in this era, they haven't wanted to give to universities as much. They feel like the NSF and the NIH are big enough, maybe. They feel like they feel some way about university overhead rates. They maybe feel like team science isn't always happening in the university as well, yada, yada, yada. So I started writing about those. And this DARPA project came up because a funder is very involved with that. And they said they hire a lot of DARPA PMs. They wanted me to kind of look into that. And I'm writing this piece up in a series of, I'm calling it like the trilogy of extremely exceptional DARPA contractors from a great era. Kind of Skunkworks is in there from the 60s, early 70s. I just wrote up BBN and kind of the ARPANET and then other stuff they did too. They were a very unique structure. And I have kind of CMU right in there as the flip side of BBN is if you have this firm, but they really care about the value structures that universities have in terms of their goals, but it is a proper firm. CMU, I kind of have on the flip side of what if you had this university that really cared about these private type team structures? Is there anything you think we should understand on a practical level? If somebody was looking to go implement these, what are specific rules of thumb that you would want to make sure the record reflected and weren't forgotten?
A couple of interesting tangents. BBN built the butterfly machine, which was one of the machines in strategic computing.
Yeah.
So the BBN butterfly, the connection machine, which has a weird history.
Yeah, I wrote them up too.
Okay. Okay. The warp machine, those were all part of it.
Yeah, you have Columbia's, the non-Von and the Dado, which were less. Yeah.
Yeah. The other tangent is Clint Kelly, who was the head of strategic computing, is still alive and kicking and loves to talk about this kind of stuff. So if you have not interviewed Clint, he's a good interview.
No, I'll read his. So I've been reading everybody. So I've actually read probably a lot of your friends' oral history. So I talked to Steve Crocker the other day. Yeah. Alan Newell's, Red Whitaker's, Raj Reddy had like 10 hours of oral histories. I've been reading a ton. Yours in particular was quite sparse in terms of like Raj had probably a 200-page oral history. Yeah. And yours was something like 15. And it wasn't, the people did it were different than the people who did some of the other more thorough ones. So I'll read Clint Kelly's and then I'll see what I would still love to know.
So Clint was at DARPA during that era. And he funded the adaptive suspension vehicle, this big 6-legged walking machine at Ohio State, funded us, got the whole, the Martin Marietta integrating contractor together. So
it seems like he helped really encode what the 3 applications were going to be.
Yes.
With an interesting history on the ALV, because with the Battle Management and Pilots Associate, it seems like the Navy and Air Force really wanted those. The Army didn't really know what to do with the ALV, but I think they saw it as a great test bed for a lot of the great work going on in the DARPA portfolio. And you can't expect the armed services to see it all the time. So they had two pretty conservative bets and then a really exciting one.
Well, so two people, Clint, at the age of 80 something or other, just went up in one of these space launch things. So he still remains very interested in these sorts of things. His idea of a good time is he produced a book on all of the world's penguins, which meant that he had to get on tramp freighters that go to these isolated islands in the South Pacific once a year. And if it happens to be sunny that day, you can get the world's best pictures of that species of penguin. The Army assigned a young captain to go tell us what we needed to do to make this stuff practical. A guy named Rick Lynch, who had just finished a master's degree at MIT and came and hung out with us and gave us good advice as to what would make a difference and what wouldn't make a difference. And Rick, as he worked his way up through the ranks, when he was running Fort Hood, he would host an annual robot rodeo for us to go down there and show off the best robotics capability that we had. When he was in Iraq, he was pounding on us. How come you guys haven't done a better job? His speech that he gave as a 3-star in the Pentagon is partly every morning I go into my office, I lay out my Bible, I lay out the 120 laminated pictures of the brave men and women who died under my command. 100 of them were doing jobs that should have been done by a robot. If you guys are as good as you say you are, how come you don't have those robots deployed? I saw Rick just in May, we gave him an honorary degree. He is now retired, but he's still very much passionate about robotics and about getting these into the Army and getting them deployed and saving lives. All right, so there's a tangent. Back to Carnegie. Carnegie had a couple of aspects of the culture. One is that doing big things and doing practical things makes a difference. So if you look at what Carnegie has done, Dwayne Adams, his first proposal he wrote was for the NavLab. The second proposal he wrote was for the Software Engineering Institute. Running an SEI, that's not a typical academic thing. But there are places like Berkeley runs the Berkeley labs and the Lawrence labs. So running an FFRDC is something that a handful of universities do, but not everybody. You don't get a lot of published papers out of that, but what you do is you provide a venue to take the basic research you've done and to turn it into practical things which change society.
And what does FFRDC stand for?
Federally Funded Research and Development Center.
Oh, okay. Thank you. I'll look more into those. I've never actually heard that term before.
So the SEI, Software Engineering Institute, does big software engineering projects for DoD, but they also do a lot of training. They also run the CERT, the Computer Emergency Response Team. So when some new virus breaks out, SEI jumps in and tells the world what the virus is and how to fix it.
Yeah.
And that's the kind of thing that is a little bit unusual for a university to do. But Carnegie had the culture to say making a real impact in society is important. And this is one way you can do it. Let's do it separately off campus so we don't dilute the graduate students in writing the papers, et cetera. But let's have this pipeline.
Yeah.
Within robotics, NASA came to us, I don't know, 30 years ago, and said, NASA's spending a lot of money on robotics. We're not getting good PR out of it, partly because our robots they go off to places like Mars. Could you take the technology that NASA is developing and work with people like John Deere? So we formed the Robotics Engineering Consortium. It sits off campus. It employs more staff and fewer graduate students. It can do confidential projects, and it takes basic research done on campus and turns it into practical projects that Deere can take and turn it into products. So that whole notion of a halfway house to take basic research and turn it into something bigger, something more practical, something applied, that this is a good thing for a university to do, that's not a universal university ethos.
So I guess a two-part question. The first part is, why do you think CMU was able to maintain that ethos so well for so long? And then the second part is, now you're a university president, so you'll have some interesting perspective on this. You have the benefits of all sorts of institutional knowledge. Why do you think schools struggle to manage projects this way, if it seems in many ways to be a natural default approach for technical subjects? Is, of course, maybe that it's weird, or it's not fully in line with regular academic incentives. Can you riff a little bit on that general genre of question?
Well, let me give you two reasons why Carnegie succeeded in doing that. The first one, I think, is really more Newell than Simon. Simon wanted to do great intellectual projects. Newell wanted to build things. So Newell caught on that building big stuff and seeing how it worked in the real world was important. And then Raj pushed that even further with it, starting out with speech, but then also the hardware projects, etc. The other reason why Carnegie did this, if you go back in the history, there was the Carnegie Institute of Technology, and there was the Mellon Institute of Science. And the Mellon Institute of Science was the contract research shop. When the Mellons owned Gulf Oil and Koppers Corporation and big chunks of various steel companies, they needed a chemistry research shop. And so the Mellon Institute was this chemistry research shop, and it existed to do contract research. If you got to produce some papers, that was good, but it was 50 PhD chemists doing industrial research. In the great merger of '67, which formed Carnegie Mellon, we absorbed the Mellon Institute and had to figure out what to do with it. And partly what we did with it was to keep it running as a contract research shop. So there was already this notion of an off-campus, sponsored by soft money, more practical research shop that we didn't quite know what to do with. But that in an ideal world, you would take basic research from the main campus and then figure out how to apply it, etc. So that was a little bit in the DNA of Carnegie since the merger in '67.
No, that's fascinating. So that sounds, it's not dissimilar to MIT circa 1920 had a program called the Technology Plan, where MIT was young, kind of 1860 to 1920. They were perpetually poor and kind of living on shoestring budgets. And at a certain point, they said, there's nothing, back then more than now, they really lived on, we serve industry above all else. That's what we're here to do. And around 1910 or 20, they said, the most honorable thing an institute of technology can do is provide a great service for a fair price. So they kind of let their applied researchers loose to work a lot of these contracts, to the point where at a certain point, what would have been their, I think, chemical engineering department, their applied chemistry department, was 75–80% industry funded, just because that's the amount of money they could bring in on these 50% contracts. So this is very interesting.
And MIT has this history of spinning out the Draper Labs and the Lincoln Labs. And again, that's stuff that's too applied to be done in a university lab by graduate students, but that should have some connection to the university, less connection in the case of Draper Labs because of some firewalls.
Yeah.
But MIT has some of that same ethos. Yeah, Carnegie had this very practical streak to it. Paul Cristiano was the provost for a while, and his dad was a Carnegie Tech graduate in civil engineering, back when civil engineering curriculum had courses like bricklaying. That this is really hands-on, get out there and get your hands dirty.
Yeah, back when they used to be able to teach industry machinists at night and things like that. at
Sure.
places like MIT or Carnegie. The different world we live in now in most cases.
So when I was director of the Robotics Institute, I said, we have won the battle to be the biggest robotics research group. We're very good at producing smart robots. We're very good at producing smart graduate students. We're not very good at producing smart industry. How do we build up a robotics industry in the city of Pittsburgh? And started working with the big foundations there, and started working with the little spin-off companies. There were a bunch of them, but none of them were very big. And started working with the university management to say, how do we pull all of this together? And when I say the foundations, like the Hillman Foundation, which is one of the richest foundations in the city, John Denny from L.C. Hillman's office came and sat with us and said, how are we going to build a robotics industry? And that led to the Robotics Foundry, and that led to Pittsburgh becoming Roboburg, which eventually led to these bigger clusters and a federal manufacturing research center and so forth.
So in that case, do you take a lot of pride in your one previous oral history, you referred the Google group, I think you maybe gave it in 2010 as Carnegie Mellon West, kind of talking about how Sebastian, of course, made his big discovery at Stanford, but he grew up at CMU. And it seems like everybody but one in that early Google group kind of grew up or had a deep affiliation with CMU. And it seems like that's held even recently. There's a lot of departments that do pretty good autonomous car work, but Uber came to CMU to essentially attempt to buy up a whole swath of the university and its projects wholesale to fold in. Do you take a lot of pride in being in the projects and people that CMU's been outputting being considered applied enough that they could be a direct input into an industrial process, rather than the current applied researchers credo at a lot of universities is somebody could pick this up and within 3 or 4 years it can be applied? You all are kind of directly plugging in.
So Matt Mason, who was on my thesis committee and was my successor as director of the Robotics Institute, he's a much more theoretical roboticist. And he says, if all of the applied people left Carnegie Mellon, we would still be a famous robotics institute for all of the more theoretical stuff that we do. But they had to kind of live in the shadow because, face it, it's much easier to do a videotape of a robot flying down the road.
Yeah.
And to explain to the Pittsburgh Post-Gazette what it is that we're up to, than it is for the theoretical people to say, ooh, and look what I can do with a quaternion. I can represent this thing. And this is a fundamental advance that people are going to be using for the next century. And they're right. And we are grateful to them. And they just have a harder time getting the publicity out of it. Sebastian, so the DARPA Urban Challenge was just a family feud. Sebastian and I have a best paper award together. Sebastian and Red have a best paper award together. Chris Urmson, who was Sebastian's number 2, was Red's graduate student. So this was just a family feud. Those guys happen to be out at Stanford, but they're still buddies of mine.
Okay, so that was all my questions for formal, and this has been absolutely fantastic. Is there anything else you would like to make sure I kind of know?
One of the great things about Carnegie is that you had Raj and Takeo in particular, who were the bosses, but who were the bosses with a very light hand. So this is great. If you can get the money to do it, go do it. If you need someone to talk to DARPA, I can go talk to DARPA, but you can go talk to DARPA. And DARPA kind of has that same attitude. They're happy to talk to the dean. They don't want to talk to the dean. They want to talk to the PIs and to the researchers and the people who are actually doing the work. And so it was not a corporate management structure where you have some boss telling you what to do. This was somewhat to the dismay of the General Motors people when we were doing automated highways. They wanted to have a steering group where the dean would
sit, and then a advisory group where the head of the institute would sit, and then the technical working group where I would sit. And Takeo said, I'm not going to any meetings. You go there and tell me if there's anything I need to do. And Raj said, oh, I'm too busy to go to the meetings. Give them my regrets, but you go and represent and tell them what I need to do. So those guys were great in setting the big picture, in running interference, and then stepping back out of the way and letting the researchers go off and do great things. So I am forever grateful to those guys for pointing me off in useful directions and then clearing out the bureaucratic issues and letting me run.
Yeah.
Takeo was very good at things like he attracted visitors from Japan. You would never in Japan have somebody from Honda and somebody from Nissan working in the same lab, but they could both come to Kanade Sensei's lab, and that was neutral territory. And he could say, oh, very nice to have you here. You go work with Chuck. And so we had this wonderful group of Japanese people working on this. And Takeo would check in on us every once in a while, but mostly it was go off and do great stuff.
Mm-hmm. I mean, and you really see that with the amount of lab alumni who have gone on to be technical leads or found a lot of these companies or research groups out in the field too.
You know, I had expected more of my alumni to go off into academia.
Mm-hmm.
If you're an academic yourself, you sort of think, shouldn't everybody want to do what I do? And no, they've gone off and started their own companies. They've gone off. Jill Chrisman was the AI guru for the Department of Defense, and now has gone back into private industry. Jenny went into academia and still teaches. John Hancock went off into the computer game industry, which is a good thing. Hardware keeps breaking for him, so we thought that actually working on real robots was not as good as working on simulated robots. So they've gone, Parag started his own company, Raul went off to Google. So it's been fun watching these guys and watching, they have this attitude that we can do it. Here's a cool problem. Let me figure out how to make something work. Oh, cool, that works. Now that it works, let me see if I can figure out how it works and write a paper out of it.
Mm-hmm.
And that's just a fun attitude and fun to watch them go and succeed.
And if it works, how do I make it usable? How can it be productized? The next step.
The next thing and the next thing and the next thing. Some of them have figured out, how do I take this and turn it into money?
Yeah.
Others have said, how do I take this and turn it into robots that run on the surface of Mars?
Yeah. And they're both extremely useful to the system.
Yeah.
All right. I'll stop the recording there.